Hello everyone and welcome to our first video lecture in our course. Uh, I will be covering in this week chapter 8. I know we have been working on chapter 8 for at least two lectures and we are almost done with it, but I thought maybe I will extend it just one more week for you to work on the homework problems. Uh, in this video lecture, I'm just going to cover maybe two or three, maybe three problems from the homework. I will work on them and then I'll show you how to solve them. And then this is probably that's the only video lecture that I'm going to do this week. And then the following week we will start on chapter 9, which is work and kinetic energy. Okay, so I believe we have covered most of the chapter, if I remember correctly. We have done. Uh, Let me go back to the hard copy, the hard copy of the book. We covered the dynamics in two dimensions, and then we started on circular motion. So, like I said, what I want to do. I just want to work on some of the homework problems. Let's see, I'm trying to navigate this ebook. We start on, let's see, I click on here. I need to take this out. And I want to go directly to problem number 17. I don't remember if I've done it or not, but let's do it again. It's right here. And it says you have a communication satellite are placed in circular orbits where they stay directly over a fixed point on the equator as the Earth rotates. These are called geosynchronous orbits. Now, a geosynchronous orbit, I think I told you about it, is an orbit that is constantly on top of a one spot on Earth. Okay, for example, like a TV satellite. Let's say I have a local TV satellite for Las Vegas, so it is always on top above us, and it's always so it's rotating with the Earth. So here we have a geosynchronous satellite or geosynchronous orbit on top of an somewhere, but on the equator. Okay. It says the altitude of the geosynchronous orbit is given by this number, and then he's asking for the period of the geosynchronous orbit and the g value. And then also he's asking for the weight of a 2,000 kilogram satellite. So let me go to OneNote here and then just type in what's given to us. Let me move this on the side. And by the way, I'm very new to this technology. I've never done any videos online or anything like that. So I have been training myself to do that. So please excuse me if my work is a little bit clumsy. I'm sure I will improve as the days goes by, I hope. Okay, so what's given to us here? He says the altitude. He said the altitude of the geosynchronous orbit is given by this number. That makes it. Think of it this way. Let me make a drawing. So if you have, for example, here is the Earth, something like that, and then you get here is the satellite right here. Okay. The altitude is basically the height above the Earth, okay, in the radial direction. This one doesn't look radial pretty good, very well, but this is the altitude right here. I'm still also practicing how to use this silly stylus pen. So the altitude, let's call it h, and this h is given to us is equal to 3.587. So it is equal to 3.58 times 10 to the 7 meters. Okay. Now remember, the radius of the Earth is 6.37 times 10 to the 6 meters. Okay, that's the radius of the Earth here. Okay. So basically, the total distance from the satellite all the way to the center of the Earth would be the addition of all that. So let me call it big R. Okay, so that's going to be the altitude h plus the radius of the Earth. And if we do that, so we have 3.58 times 10 to the 7 plus 6.37 times 10 to the 6. And if you calculate that, I've done that already, it is 4.22 times 10 to the power of 7 meters. Okay, so that's the total distance to the center, from the satellite to the center. Okay. Okay. Now, he said, what is the period of the satellite? So what is the period here? Well, I think I solved this problem in class, if I remember correctly. Anyway, so he said, what is the period? Period. Tau. Since it's a geosynchronous orbit, so that means the satellite is constantly on top of on that spot on the Earth, so it is going around with the Earth, and of course the period of the Earth is 24 hours, right? So the period of the satellite would be 24 hours. Of course, you want to convert it to seconds, so just 24 hours times 3,600 second. That is 3,600 second in 1 hour, and then you would calculate that. Okay. B. B says find the g value at this altitude. Okay, so basically we want to find the acceleration there. Well, we know that the acceleration is equal to, there's several versions for it. One is v squared over r, right? Another version for it, we know that v is omega r, so that's omega r squared, make it big R, over r, so that makes it omega r, omega squared r. Okay, so that would be one way to calculate that. Of course, I want to calculate omega. I know that omega is 2 pi over tau. Tau I already calculated for you right here, right? So that's just going to be 2 pi divided by 3,600 seconds times 24, and then we do the calculation of this, and then let me use my calculator. Bear with me. So I have here 3,600 times 24. That gives me that, and then I had divided by 6.28. And then if I did it correctly, I have 7.2. Please check my work. If I did it correctly, I have 7.27 times 10 to the power of -5 radian per second. Okay. So with this in mind, so in this case I can go and calculate the acceleration, which is equal to omega squared r. So that will be this number, 7.27 times 10 to the -5, multiply this by squared times the radius, which we got to be equal to there it is, 4.22 times 10 to the 7. So that will be 4.22 times 10 to the 7, and then when we calculate this acceleration, it turned out to be 0.223 meters per second squared. Okay, got it, everyone? And then part C here, it says what is the weight of a 2,000 kilogram satellite in a geosynchronous orbit? Now this is kind of a trick question, since there is no surface where the satellite is sitting on, if you will. That means there is no normal force. In this case it will be weightless, so in this case it is basically weightless. So the weight here, mg, is, or let's call it weight w, is equal to 0. Okay, so we have no weight because no normal force, no normal force. Okay, simple problem. Okay, all right, let's move on to the next one, a little bit harder. Number 19. I think it's homework as well. It's right there. Number 19. think I can make this one big page. There we go. Okay, that's better. And I'll lift it up. I discovered a trick that I can lift it up with my hand on the screen. I'm a Mac user and I'm using a PC, so I'm also this is an added difficulty that I have to be familiar with Windows 10. I haven't used it in many years. Anyway, number 19. It says the weight of a passenger on a roller coaster excuse me, increases by 50% as the car goes through a dip with a 30-meter radius of curvature. What is the car's speed at the bottom of the dip? Okay, let me draw a diagram here for you. So it is you have that dip that looks something like that. Here is the passenger right here, as he or she moving in this velocity like that. Here is the center of the curvature. Here's the radius of curvature. You got the weight of the guy moving, and then you have the tension, right? So the tension is going, if I can make it vertical like that, there we go. This is the tension, okay? As it's moving in this direction, in the tangential direction, that is. Okay, he said the weight of the passenger increases by 50%. So now if I would put the sum of the forces here in the radial direction, sum of the forces in the radial direction is equal to ma. A here, of course, is the centripetal acceleration, so that's sum of the forces in the radial direction equal to mass of the guy divided multiplied by v squared over r being the radius right there, right? And this basically we have here the tension minus mg equals to, well, this whole thing increases by let's forget about this for a minute. Let me just talk about forces here. Forget about this for a minute. So you have this tension minus mg increases by 50%. So that's the difference between them is now 50% of the weight. That'd be one way to think about it. Okay, so now I have T minus mg equals 0.5 mg. Sorry, I can use an eraser here. Mg. So therefore the tension is 0.5 mg plus mg. So the tension in this case is 1.5 mg. Okay, that's the trickiest part about this problem, is finding the tension. Okay, so now I found the tension. Now I go back to this formula right here. Okay, here. So I have the radial direction. I got two forces, T minus mg equals ma, which is mv squared over r. So I have 1.5 mg, that's for the tension, minus mg equals mv squared over r. And with that, the masses cancel out, right? And I am solving for the velocity. You can work out the algebra, and if you work it out, you'll end up with 12 meters per second if I did it correctly. And there we go. Got it? Okay. The next problem is the homework one, number 47. It's a homework for those of you who haven't. We have not done that, I'm sure. Number 47. Sorry for the clumsiness. I'm sure I'll improve later. Let me scroll down to 47. This is the book. There it is. And this is the associated picture to it. Okay? So what you have in here, he says a canonical pendulum, there we go, is formed by attaching a ball, here it is, of mass m to a string of length L, here it is, then allowing the ball to move in a horizontal circle. So it moves in this circle like that, okay? Okay. And then he said, find the expression for the tension T in the string. Okay, so we have a tension in the string. And then also find that expression for the ball's angular velocity, omega. And then he said, what is the tension? And he gives you numbers. So you can do the numbers. Basically, we want to find an expression, symbolic expression, and then you put in the numbers to get the answer. So I'm going to do part A and B, the hard part. The easy part is part C, right? So let me make a drawing of this thing. So it looks something like that. So here is the canonical pendulum, or conical pendulum rather. It looks like this. I'm trying my best to make it nice and circular. Here is the mass right there. Here is the length, L. I like small l. Here is the radius, R. Okay. And then, of course, this is the apex of the pendulum, and it has an angle, the apex angle. We're going to call that theta for now. Okay. He didn't give it to us, but we're going to call it theta for a good reason. In a minute he'll show. So what are the forces here? Well, we get the tension, which is along this the string. Here it is, T, and then you have the weight. I'm trying to make it vertical as much as I can, like that. Okay. So if I take, let me draw it again here. So if I have, here's the ball, here's X and Y. Okay, let me draw X and Y first. Here's X and Y. Here's the ball. Here is the tension, T. And this is the weight, mg. And of course, this angle would be the same as the half apex angle, right? This angle right here is the same as the angle here. You agree with me on that? So in this case, oops, what am I doing? I want to make it, oh, there we go. Okay, so in this case, I will have so this is mg. If I call this x-axis and this is the y-axis, so in this case, I have a component t sine theta. Then I have here t cosine theta, correct? So now, so the sum of the forces in the x direction is 0, because it's moving in a circle, and the bob or the mass m here is not moving up and down, so that should be 0, right? So in this case, we would have minus t sine theta equals minus t, I'm sorry, I wanted to say on the y direction, okay, I'm sorry, in the x direction, it is not, I mean, it's in the y direction, it's not moving up and down, so that's the y direction, not the x direction. I mean, I made a mistake here. This is in the, let me make it, sorry. In the y direction, it's not moving up and down, so that's 0. Let me just take it, oop. Let me erase that. Let me talk about the y direction first. I'm confusing things. Okay, so nothing is, so in the y direction, we would have here what? T cosine theta equals, sorry, minus mg, right? Equals 0, right? Remember, he said in the problem, he said find an expression for the tension. So I just need to find an expression. Okay, so with this in mind, I can say that the tension is equal to mg over cosine theta. So somehow I need to eliminate cosine theta. Now if I go back here, let me go back to the cone right there, right here, and if I would draw how the cone looks like, in other words, if I, here's the, I have a triangle here, here it is. Here's the mass, right? Here's the angle theta. This is L and this is R, is that right? So in this case, cosine theta is equal adjacent over hypotenuse, or the hypotenuse is L, right? The adjacent is L squared minus R squared under the root. Is that okay? And let me just do sine for now, once and for all. So we have sine theta, that be equal to opposite over hypotenuse. So that's just going to be R over L, right? But I can also argue that R is L sine theta. But anyway, that's for later. So anyway, so we have those two expressions. Now let me go back here, and then if I calculate the tension, it's going to be mg over cosine theta. Well, cosine theta is that, so that's going to be, the tension is going to be mg L over square root of L squared minus R squared. There we go. Okay, so that would be one expression. This is basically the expression that he's looking for, I believe. That's for part A. Okay, now let's do part B. Part B, he says, find an expression for the ball's angular velocity, angular speed, omega. Okay, so now let me go to the sum of the forces in the x direction. Well, in the x direction, it's moving, so you have a centripetal acceleration, so that will be mv squared over r, or maybe I could write it as m omega squared over r. Why omega? Because he's once omega, so I'm going to write it in this form. Okay. Okay. Now, so what are the forces of the x direction? Let me go back to the drawing. In the x direction, I only have t sine theta. That's it, instead of saying. So in this case, I'm going to have here t sine theta equals to m omega squared r. Okay? And then I also have an expression for sine theta is right there. Okay? So I'm going to take that, plug it back in there, and then I also have an expression for the tension. So I'm going to take the sine right here, this one, and the tension. I'm going to plug it back in here, and then do the algebra. That'll be a lot of algebra, but it's simple. So all I need to do, all I need to do is, I'm moving it with my hand. Okay, when I calculate all of this, so for the tension, so it's going to be mgl over square root of L squared minus R squared times sine theta, which is R over L. I'll leave it R over L for now, equals m omega squared R. The R's cancel, which is nice. Okay, and then I have the L's cancel. So I'm left with, and the M's cancel, there we go. So therefore, omega squared, I'm going to get it from here, is equal to g over the square root of L squared minus R squared, or I can say that omega is equal to big square root of g over square root of L squared minus R squared. It's not the prettiest expression, but that's basically what we got. Got it? And then that's it. I think this is the expression that he's looking for. And then part C is simple. He basically says, he gives you numbers. He said, what are the tension and angular speed of a 500 kilogram ball, so that gives you the mass, swinging in the 20 centimeter radius at the end of a 1 meter long string. So he gives you L, R, and M. Between those three, you can get the tension without any problem. You have everything. And then with that, you can also get the omega, the angular velocity. Got it? And that's it. We'll stop here as far as this problem is concerned. The next problem that I want to do, and I think it's the last problem, let me look up my notes here, my lecture notes. I wish I was in class rather than being online like that, but anyway, There's one more problem I wanted to do. I'm trying to remember which one. Oh yeah, number 56. I believe I did part of that problem in class. And I think it's homework. Let me go to mastering and see if it is homework or not. Um, homework 8. Let me just click on it. It's 56. It is not homework. Oh well, that's all right. We're gonna do it anyway. Okay, 56. Here it is. Okay, the problem says, let me make this a little bit thinner. The problem says you have a 100-gram ball, so you have a mass of 100 gram, which is basically zero point 0.1 kilogram, ball on a 60 centimeter long string. So I have a string of 60 centimeters, so that would makes it a radius. So 60 centimeter, that makes a 0.6 meter. It's swung in a vertical circle about a 200 centimeter above the floor. Oh, there is a picture right there. Sorry, here's the picture. Okay, so the tension, keep me signed in. I think this is mastering is warning me. Oh well. Okay. He says the tension in the string when the ball is at the very bottom, right there. Okay, of the circle is 5 Newton. Okay, so that's the tension. Is 5 Newton. Then he says a very sharp knife is subtly inserted to cut the string directly below the point of support right there. There is a knife right here. How far to the right of where the string was cut does the ball hit the floor? Okay, so basically here's the story. Let me expand that. Let me draw a picture of that. So what you have in here is something like this. I have here's the I'll put it here. Here's the circle. I can make a really nice circle on the board, but here I'm not very that sharp. Okay, and here is the ball. This is the radius r, and it's moving with velocity v. Okay, and it's moving in this fashion. Then here's the bottom right here. You get the velocity this way, same velocity v, right? And then you get the knife, sharp knife here. Here's a sharp knife. It cuts it. So what will happen? Here's the floor, okay? And he says from the center here to the floor is 200. Is that right? Let me go back to the drawing. 200 centimeter, right? Okay. So here we have 200 centimeters right there. 200 meter or centimeter? Hold on, sorry. 200 centimeter, okay. So that will be 200 centimeter, that makes it 2. Anyway, so you have centimeter all the way down there. So then the knife cuts it. So what's going to happen, this ball is going to move in a projectile motion and it hit the floor here. Nice parabolic path. There we go, right there, okay? And of course, this distance makes it 140 centimeter, right? Why? Because the radius is 60, remember? Here it is, right there. Okay? So he says, how far does it go from here to it? That basically, it's two-part problem. Of course, this is the height y. It becomes a projectile problem. So my goal here, with this information, I need to find v. And once I find v, the rest is just kinematics, projectile kinematics, okay? So to find v, I need to use dynamics. So we're going to start from here where the ball is right there, and we ask the question, what are the dynamics here? In other words, At bottom, we have the sum of the forces is equal to MA, right at the bottom right here. What are the forces here? Well, I have a tension T and I have the mg. Is that right? So here I have T minus mg is equal to mv squared over r, right? R being the radius of the circle. And then from there, and by the way, T is given to me right here. G mass is given to me as well, and the radius is given to me as well. So I can easily find V. The V in this case, I just kind of copy it from my notes. It basically, after you do the algebra, it is R over M, parenthesis T minus mg, and then you plug in your numbers, and you will get 4.91, excuse me, meter per second. Okay. So in this case, let me lift up the page. So this, as far as, let me go back to the diagram. As far as this diagram is concerned, this becomes like, after that, this is going to be a projectile problem. This we can call it, let's say, V naught. So basically what I have the following picture. Here is the height. Here is the ball right here. It's moving with some velocity V naught, which is this one right there. Okay, and we have a projectile problem like that, so I need to find x. And of course, it is g here. So it's a free fall, if you will, right? And the height is y. Again, I can calculate that. It's just 140, so that would be, what is it, 1.4? Yeah, 1.4. 1.4 meters. Okay. The rest is just like I said. So the first thing you need to do, I know the y, so horizontal motion. We've done that in the past. Vertical motion. The horizontal motion would be x equals v naught xt, which is this is v naught x, right? It's moving horizontally, and then y would be y equals v naught yt minus 1/2 gt squared. V naught y is 0, so you have y equals minus 1/2 gt squared. And then this v naught x is already calculated right there. And he wants x, so how do we do it? Well, we start from here. We get y, it's basically 1.4. Be careful, it's below the datum, so it's negative. 1/2 minus gt squared, and then I'm going to solve for t. The time in this case will be 2. Did I solve it? Yes, it is 0.535 seconds. Okay, and then we take, trying to find the correct right here. So therefore, x is equal to v naught xt, and therefore I'll just scratch it like that. X equal v naught, which is we have just calculated 4.91 times the time 0.535, and then we calculate the distance traveled is 2.63 meters. And there we go. Got it? And that's it I wanted to talk about. Please let me know if you have any questions. And like I said, let me just go back to the class. We are in Physics 180. And I have the course is already published. I hope you have noticed that already. Please take the time to read Module 0. If you have any question, you can either click on Ask the Professor like that, and then you just post your, just click reply, and then you put in your question. I'll be checking this regularly. Another option is please use this email, not the UNLV. I prefer if you use this one. Or you just click it, and then you just type in your question. And like I said, I will be checking it regularly. This is the course schedule. I have already sent it to you, so I'm sure you already know about it. And then the Student Cafe is just a discussion forum just for you guys if you want to talk to each other. I am not going to be going there at all. So that's just for you. It's totally optional. If you don't want, that's fine. And then module one is where we start here, and it's, remember, all the assignments are due on next Sunday, March 29th. And I'm going to be adding the this video here. You're going to see it as a 1, 2, 3, 4 as a fifth item. I'm going to be adding it today. There is also a lecture that I have posted for Professor Lewin. If you are interested in learning, he's excellent professor. He's done those lectures back in 1990s, if I remember correctly. If you need to learn more information, he is very, very good at that.
Today we
At the
will
MIT.
discuss what we call uniform circular motion.
Anyway, he goes on. You're welcome to. You're not required, but they're very, very helpful lectures. Okay, that's it. You have a wonderful day, and please let me know if you have any questions. Bye bye.